The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Good afternoon, ladies and gentlemen. It's my great pleasure to be here today. I'm really sorry I have a severe cold, so my voice will not be very clear, but I'm excused for this. And also the title here is a little bit different from what you have on the brochure for the ACI. The reason for this, when we first submit the abstract for the session, this is work in progress, so we only tested few columns, and now we have more data, so I included more data over here and slightly changed the title. This is part of PhD student work, Ayman Mustafa. This is the outline for my presentation, short introduction followed by material properties and experimental program, results, and conclusions. First of all, as you have seen on the last couple of presentations, if you have conventional concrete, reinforced concrete columns, what you would get either failure under severe earthquake, or you may get significant residual displacement. So we try to look at a solution for this in using two different approaches. One approach, what we call external solution, using post-tension segmental. So this is very much similar to what you have seen on the first presentation on this session. The other one, what we call internal solution. And what I meant by internal solution is why we insist to use just concrete. Can we add any other material to concrete to change the characteristic of concrete, to increase the energy dissipation and make concrete dissipate more energy? What we look over here is looking at to mix with concrete to replace some of the fine aggregate with rubber. So we use scrap rubber as a replacement of sand, fine aggregates. And with this, we hit two birds with one stone. First, we approach more like, find a place for scrap tires, and the other is to make more meaningful use for rubber. The other option is to use the segmental construction, and with segmental construction, we add one more thing, which is the hollow core columns. So what we use over here is a segmental, but also it's a hollow to make it easy for construction. As I mentioned, with what we call rubberized concrete, so it's a very regular concrete, we replace part of the sand on the concrete with the scrap tires. And with this, we have a more green construction. Do we have scrap tires available? Yes. The short answer is yes. We have about 200 million scrap tires each year went to landfills. We used to use this in cement kilns as a part of the fuel, but in the recent few years, EPA changed their regulations, and we cannot use most of this into the cement kilns anymore. So this is make it more a problem. Right now, we use about 4% only of these scrap tires into civil engineering applications, and when I say civil engineering applications, mainly in pavement. What's the issue with scrap tires? It has a very long durability. So when it goes to landfills, it stays there almost forever. So, well, it could be a good thing for us. Durability is an issue for civil engineering. So we can look at this from a civil engineering perspective as a positive thing. The second thing is it's very, as you see over here, a couple of years ago we have a fire in scrap tires in Missouri State, and it takes 25 fire departments for 3-4 months try to extinguish the fire, and they cannot. What they did is just cooling around the site, just to be sure that it will not extend to anywhere else. So it's a serious issue if you get tires. As I mentioned, we only use about 4% of this. So what is the advantage? There has been some research on rubberized concrete at a material level. So on the material level, there has been some research showing, it would increase the ductility. And also, there has been some research on impact, showed that rubberized concrete has a better impact resistance, soundproofing. So a lot of good stuff, but unfortunately, we don't have enough structure testing. We're looking at all this stuff, comes to my mind, probably it has something to do with energy dissipation. If you have a soundproofing, it has a higher impact resistance, all this nice stuff. It has something to do with more of the viscous damping on the material level. So we try to look, is there any benefit of using this as an energy dissipation into the material level itself? Well, this is one thing. This is related to the internal solution. And now we move to the external solution, which is the segmental construction. And I'm not going to repeat what you heard before in the first presentation. With accelerating bridge construction, there is a strong momentum right now in the US to develop accelerated bridge construction. And you would get all these benefits over here. The cross-section that we decided to use over here is a hollow core section. So on the outside here, we have a fiber-reinforced polymer tube, and on the inside we have a steel tube, and in between we have concrete. So this is a small scale testing, so we tested about 4th scale testing, but if we think about a full scale, like a 5 feet diameter bridge column, what we propose is probably 3 inches of concrete sandwiched between the steel pipe and the FRP pipe. So think about the huge reduction in terms of the weight of the column. And think about something like freight cost. This would be precast, right? So think about freight cost. And we used a post tension to allow small residual displacement. And also, we need more experimental work. Probably we have a very limited experimental work in terms of dynamic. There has been some research, analytical and static cyclic, but dynamics, we don't have too much into segmental construction. And as you have seen also in the first presentation, with most of the rocking system, you need some energy dissipators to combine the post tension. Otherwise, you would get a very limited energy dissipation, which make you have a higher demand into displacement into your columns. These are the two systems that we propose, the internal and external. Over here, we're looking at, we started from a very basic research here. We start looking at the material level for what I call the internal solution, looking at the rubberized concrete. So we have here two different sets of materials. The first one, which we call CS, which is a constant slump, and here variable slump. So what we have here, we have the percentage of replacement of sand. So let's say this one here, we replace 10% of the sand with fine rubber, and so on. And we look at the slump over here. If you keep everything is the same, as you keep increasing your rubber content, there is a reduction on the slump, which make it almost you cannot use it for construction. So what we did is we play with the super plasticizer. So everything is the same except the super plasticizer. So we played a little bit with the super plasticizer, and we were successful to get almost a constant slump for up to 30% replacement, which is a very good percentage of replacement. The second effect, we looked at the compressive strengths, how the compressive strengths would be affected when we replace different percentage of the rubber. And we look at two different things here. We look at 7 days and also 56 days. And for the two sets, the variable slump and the constant slump. Why we tested at 56 days? Because this one here, we have a high strength concrete, so we have a lot of fly ash. And as you know, fly ash is very slow in gaining strength, so instead of testing at 28 days, it's more common when you have a high amount of fly ash to test the strength at 56 days. Based on this one over here, we started with approximately 80 megapascal, and if you look at the reduction here, we would say probably up to 20% you get a reasonable reduction in strength, and keep in mind this is just a concrete compressive strength. Now when you go to a subsystem testing, which is a column, you would probably get a smaller reduction on the lateral strength of the column. And then the other thing that we did is looking at the damping. And here we just present one graph. We have actually published one full paper about the damping characteristics of these two materials. The way that we measure damping using too many approaches, falling weight, mass falling weight, we use also a hammer impact, we use some non-destructive testing, so we use a lot of things to measure the damping. But this is kind of our conclusion here. And again, this is a very low damping because we measure for the elastic range and at the material level. So if we have a zero rubber here, you get close to 1%. If you go to 20%, you get approximately 1.5. So it's almost 50%, up to about 50% increase into the viscous damping. And here is the effect on the modulus, the dynamic and the static modulus with the rubber content. The next step is rubber is very sensitive to loading rate. So we'd like to see how the loading rate would be affected. We think about seismic dynamics, so high loading rate effect. How the loading rate would affect the response of the rubber. So what we have over here is we're looking at, again, different strain rates. And over here we have the compressive strengths. But this is not just a concrete cylinder. This is a confined concrete cylinders. So we have this is a concrete. It's confined into FRP. And we play with the strain rate. And over here we look also at ductility. We're looking at how much is dissipated energy, again with different strain rate, and also we look at the damping. So strain rate doesn't really make anything like weird on most of them. The only thing that really still interesting is still see this is the equivalent viscous damping with no rubber, and again you still see almost 50%, and if you go to higher strain rate you even see more, almost double the one without rubber. So all the tests that we carried out, there is a beneficial use for rubber over here. Here is our test matrix, and as I mentioned, we haven't done yet. This is a work in progress. Over here, this is a little bit different from what you usually see. You would see we're testing one column and then changing one parameter, moving to the second one, a third one, and so on. Over here, we are comparing a system to system, response to response. If you are going to design a system, this would be your column here. If you are going to design another system, this would be your column here. So the first column over here, this is what you use these days. So this is a well-designed, state-of-the-art design for a conventional reinforced concrete one. This is very much the same, with the only exception you have 20% replacement of the sand with rubber. The third one here is a segmental column. The fourth one, a segmental with energy dissipation, the energy dissipators. All of them has the same diameter, which is 12 inch. I think this is about 1/4, 1/5 scale. And these first two over here having a solid cross sections. The segmental here, as I showed before, they use a hollow core section. So it's a steel pipe inside and then the FRB outside. And over here for the external energy dissipation, we have number 4 external bars, and you would see some picture of this on the next slides. And then we tested all these specimens on a shaking table. We have a shaking table at Missouri University of Science and Technology. And again, we're looking for something aggressive, so we selected a near fault ground motions, which is Rinaldi stations. And this is the spectrum after we scaled the spectrum for our test. For construction of the test specimens, here is the segments, and then we did cast matching between the segments. So in other words, you bore the first one and then wait until it's hardening, and then you bore the second one on top of the first one, so you get the same surface between both of them. And here is our technicians, very dedicated, try to fix the post tension here for the segmental column. And here is the mass. So this is the column now on top of the shaking table. Here are the mass. The mass over here consisting of 2 parts. The first part is the concrete filled steel tubes, and then we have a heavy reinforced concrete head over here. And both of them are post tension together. And this is different from the post tension of the column itself. So this is just post tension of the mass with the head. And here are the energy dissipators. As I mentioned, we have number 4. So these bars are from the 4 sides of the column, and then it is a tension-only dissipators. Just to avoid also the low cyclic fatigue of the bars, we use a tension-only dissipators. That's mean we have the bar over here, and it's connected to, as you see, a heavy angle, and we have a nut over here. So if this bar is in tension, it will expand and probably yield. And if it's in compression, it will just slide into the steel angle. And the steel angle itself is welded to the inner steel pipe. It looks ugly, but we're working on find a solution for the shape of this. But again, the advantage is it's outside, so it's easy to replace. After an earthquake, if you have a yielding and damage to the energy dissipators, you can replace it. And here the reinforced concrete one. This is a conventional one. And you can see this is not the last test. This is 150% of the Rinaldi. So you can see over here it's clearly the residual displacement of the column. This is the one with the rubberized concrete, the segmental one without energy dissipation. So you see it's more flexible. If you look over here, there's an opening and the closing of the joints without really any significant damage. And you will see more qualitative numbers on next few slides. It's the same column, but for some reason the video here is very distorted, but the same height, everything is the same. This is the one with the energy dissipators over here. Well, here we are looking at the response for different ground motions. So what you have here, you run the shaking table and you just measure how much force. And the way that we measure the force, we have accelerometers at the mass level, and we have a mass times acceleration to give you your force. And this is your lateral force, and you measure the drift at the center of mass as well. So This is the one at reinforced concrete, and we run the test starting at 10% acceleration of Rinaldi and keep going up until 150. And what happened at 150, we get rupture of the flexure rebar. Well, this is well designed, so the good news, it passed the 100% of Rinaldi and even went 50% beyond this. But you still get rupture, and you see over here, this is the residual displacement over here. This is the one with the rubberized con column at the same earthquake, which is the 150. The good news over here, we reached 150, no power rupture. And we're able to go beyond this 5 more test runs. So we tested this up to 200. And in terms of damage, this one was much better. It was more fine cracks, more distributed compared to the regular reinforced concrete one, thanks to the rubber. This one over here, this is the segmental one. Qualitatively, you can see over here there is no much of residual displacement. We'll see this more qualitative in a second, but over here you can see there is no much damage on this one over here. This one with the energy dissipators, unfortunately, I will stop at 100%. We have some problems with the energy dissipators connections, so I'm still working on this, try to fix it. Here is we get the dynamic backbone curve. So for each test run, we get the big strength and big displacement, and we plot the force versus displacement. The green one over here is the segmental. The black here is the segmental without energy dissipators. And here are the two with the rubber and the conventional one. What's really interesting, this is the reinforced concrete stop here at about 4.5. The other one, the rubberized, was able to go through 6%. In terms of strength, you can see over here, this is the one without rubber, this is the one with rubber. There is no much difference in strength. This is what we did all the tests to look at, the energy dissipators for both of them. So here is the regular reinforced concrete one, and this is the rubberized column. And here we have the different percentage of the ground motions. And clearly out of, starting from 50% at the beginning, there is no damage, so you don't have too much difference. But starting from about 50%, you would see that consistently the reinforced concrete dissipates smaller energy compared to the rubberized one. And at rupture, starting when we start rupture over here, we have a difference of about 16% of energy dissipation between the rubberized and the conventional concrete one. Here is the one with energy dissipators and the one without energy dissipators. Both are segmental. So clearly over here we see much higher energy dissipation compared to the regular concrete, the one without energy dissipators. Over here we try to look at the residual displacement. So we have the reinforced concrete compared to the segmental without any energy dissipators. So in terms of peak drift, the demand was very much the same. However, again, all this is this, so you go back and forth, drift versus time here, so you go back and forth until you almost done with the earthquake, and now all this is your residual displacement versus over here you almost get nothing. So after 25 earthquake, you can look at this as foreshock and aftershock earthquake. So for 25 earthquake, we only have residual displacement of 0.03%, which is almost nothing. For the reinforced concrete one, we get 1.5 after only 20 earthquake excitations. As you heard on previous presentations, typically, after Kobe earthquake, they demolish most of the columns that have residual displacement more than 1%. If this is the case, this one would be probably demolished, versus this one would be probably kind of repair. And now for the rubberized concrete versus regular one, here is also looking at the residual displacement. They behave very much the same, and here we start to see some yielding and more rupture on the reinforced concrete. So this is why you see more of a higher displacement into the residual displacement in the reinforced concrete. The rubberized one is still working much better, and then all of a sudden also at 190 you rupture your bar into the rubberized concrete, and this is why we see a huge increase on the displacement. Here we look at the damage. So this is the vertical line over here. This is just to indicate the residual displacement visually. And here is the rupture that happened at 140% for the conventional concrete. Very much the same here, but happened at 190. And here is the rupture on the rebar for the rubberized column. And this is the segmental one, vertical. With this, I reach to the conclusion of my speech here. Scrap tires. We can find a home for scrap tires. At least part of it can be used on reinforced concrete in high seismic zones in other dynamic applications. Segmental double skin is probably a very good alternative for conventional construction. As also you heard on the first presentation, we measure the time for the construction of this one. It's about 10% actually from like a conventional concrete. So it's really a huge reduction in terms of construction time. The segmental column has a more flag shape of hysteretic behavior. That means we have a self-centering with small energy dissipation, and this is why we substitute with some external dissipators. The rubberized concrete increased energy dissipation by 16%, and I just would like to thank you so much.